We have been considering this week partial differential equations connected to the modern theory. And let us now focus on some essential parts of what we have learned. One very important part of this theory is connected to the establishment of weak formulations of a strong formulation. Strong formulation is just a partial differential equation in the form that we learned in the first week. It's defined on some subset omega, which is most often a bounded subset of Rn. Then we multiply with some test functions on both sides of the strong formulation and integrate over omega. And then we obtain a weak formulation of this type. Or not weak formulation actually, but this is the fundamental basis for the weak formulation. Because when we are using the Green's formula, we obtain a weak formulation of this type. In this process, we also add information about the boundary conditions. This test function phi, which we are multiplying with, is in some subset of the Sobolev space W12. Sometimes this subspace is this space W0 with zero boundary conditions. For the Dirichlet problem, for example, this is the case. And for the Neumann problem, we use the whole space W12. We have periodic problems where we, in these cases, we use W periodic. So we have given you examples of three types of problems or boundary conditions where we are using different types of function spaces where this test function should belong to. We are then asking ourselves, does this weak formulation have a solution? And this brings us to the existence theory. And in the existence theory, we use some general space, capital V, which is a Hilbert space. We use a general bilinear form on this Hilbert space, and we have a linear form on this Hilbert space. And we are asking ourselves if these four properties are satisfied. The first is connected to the symmetry of the bilinear form. The second is concerning the continuity of the bilinear form. The third is connected to the V-ellipticity of the form, this bilinear form. And the fourth condition is devoted to the continuity of the linear form, or the functional L. We also have some equivalent minimum formulation, which takes this form. Always on this f of phi is always half a of phi minus L of phi. And we are asking ourselves to find if there exists a solution u such that f of u is equal to the minimum of f of phi, where phi is taken over all these values in this Hilbert space. This the abstract weak formulation, which is on the same type as we have described earlier, takes this form, and we know that from the theory, we know that these two formulations are equivalent if all the properties A to 4 is satisfied. satisfied. Moreover, if the property 2, 3 and 4 are satisfied, then this problem has a unique solution. So these two results are called the Lax-Milgrams lemma, and the other theorem is not called anything, but it's connected to the equivalence between these two formulations. So Lax-Milgrams lemma is the one connected to the existence of a unique solution to this weak formulation. So in the course we only consider the case when this bilinear form is associated with integral formulations. So let me just emphasize that we only have considered cases where this capital V is a subspace of this large Sobolev space, and that where these bilinear form and linear form are defined by typical integrals, which we have seen many examples of. So let us now say some more about these four conditions. The first condition connected to symmetry is always very easy to show. The second condition is connected to the use of Schwarz inequality, which takes this form or this form. We are often using both these inequalities. The third property connected to the V ellipticity is often proved by using the Poincaré inequality or the Friedrich inequality. So when we are have a problem where the boundary conditions are zero, we usually use Friedrich's inequality. Otherwise, we have to use this Poincaré inequality. In order to prove the property 4, we also use Schwarz inequality. We have one important application of the abstract theory, which is called the finite element method. In the finite element method, we replace the weak formulation by we just replace the space V, which is generally in finite dimensional, with some finite dimensional subspace of this space, and in this space we search for a solution in the same way as we did in the general problem. The main difference is that this problem is much easier to solve by computational methods, and the way of solving it is just by using making use of this expression, because h is given by the base vectors v1 to vm in this finite dimensional subspace, and we multiply with constants or real numbers xi1, xi2, and so on, these basis vectors, and add them. So finding these real numbers gives us the solution. So in order to solve this equation, this problem, we have to solve this equation where A is a matrix with components A, ij, were given by this bilinear form of the base vector vi and paired with Vj. And this B vector is just components consisting of components bi equal to L of Vi. So when we compute all this, we are able to find the solution of the finite element problem. So this is the main points in the modern theory of partial differential equations in this